which happened to be my research area. I wrote a paper with a student before, so I thought maybe I'm going to talk about Sachs Wolfe effect using my own research. So as you know, as we're talking about, this is the total energy budget of the universe, and then this 75% is something called dark energy, which is pushing the expansion of the universe, but we don't know what it is. So this is, one of the biggest mysteries in physics. And then, as you know, people got Nobel Prize on finding this dark energy. And then, so it is very important to test it in every possible way, not just supernova, but we should test it in an independent way to make sure this really exists. One example is this: how reliable is supernova? So this is a plot that got the Nobel Prize from supernova cosmology team. So this is basically showing how to diagram. So as a function of redshift, do you see my cursor? Or you don't? So I should do this way. Then you see. Right?
Yep.
Okay. So as a function of redshift, this is the magnitude of the supernova, right? Then supernovas get, if you go higher redshift, magnitude of supernova, this type 1a supernova gets fainter and fainter and fainter. And then the reality is it was getting slightly more fainter than expected. See? So if you take a difference, this is now delta as a function of redshift. Instead of what's expected without dark energy, this is horizontal line, the data points are a little bit above, right? That's because the supernova is a little bit fainter than expected. That's because, and then their interpretation is that's because universe's expansion is getting faster, accelerating. So that's the discovery of dark energy. But as we can see, the scale of the points are very large, isn't it? So some of the supernova data are even consistent without dark energy here, right? So that's why another way to test, is this really okay? Is there really dark energy? So testing using independent method is important. And one way to do it is integrated Sachs Wolfe effect. Okay, let me explain the integrated Sachs Wolfe effect. So here comes the CMB photon. That's our familiar subject, right? We're talking about CMB photon for many weeks during the past. Then CMB photon comes towards us. So we are on here, and the CMB is coming from the left. And then suppose here's a gravitational potential, something like a galaxy cluster, or even larger scale. Okay? Then if there's no acceleration of the expansion of the universe, the photon go into the potential, and it comes out, and then gets to us. When photon fall into the gravitational potential, it gets energy, right? Gravitational energy is transferred to photon. But it loses the same amount when it gets out of the potential. So the net energy is the same from here to here without dark energy. But if this dark energy, when after photon fall into the gravitational potential, because of the expansion of the universe, this gravitational potential gets a little bit shallower with dark energy. So photons going to climb less potential than going in. So photons going to net a little bit of plus energy when it gets out. This is called integrated Sachs Wolfe effect. Obviously taking the name of the people who discovered Sachs and Wolfe. Okay, so this is called Sachs Wolfe effect. So if you So this is animation. It's showing this integrated Sachs Wolfe effect. So this green screen it's CMB photons. So CMB photons come into us, and then when it goes into potential, it gains energy and then loses energy. But then as you can see, while photons in the potential, the gravitational well is getting shallower because of the expansion of the universe. So in the end, the photon is getting energy in the center here. So the colors changed at the center, right? Because photon got energy because it's climbing a little bit shallower potential. So if you detect this effect, then that's, in other words, it's a proof, independent proof of dark energy. Is this Sachs Wolfe effect happening or not? Depends on dark energy, right? So let's test it. How do you do it? If you do it mathematically, it's something like this. Okay, this is what I explained, written in mathematics. Okay. Then, so here I wrote a paper. So the way to detect this, the individual effect is very, very subtle. As you know, CMB has its own fluctuation, right? So integrated Sachs Wolfe effect is actually something like 1% of this fluctuation. So this fluctuation is small, but then integrated Sachs Wolfe effect is even smaller. So individual ones, we cannot detect it. If you look at a galaxy cluster, oh, here's an ISW effect, or no, we cannot tell. So we need to do statistically. So we cross correlate with galaxy density. So by the way, this is the galaxy density map from WISE All Sky Survey. Okay, so you see the darker colors are higher density, higher galaxy density. So the very dark places or very red places here is the place of galaxy clusters. Okay, and then if you cross correlate with WMAP, if there's an integrated Sachs Wolfe effect, these high density regions, then integrated Sachs Wolfe effect is going to happen, right? So there should be a cross correlation between CMB temperature and then galaxy number density. In dense regions, high galaxy density, CMB temperature gets higher or lower? Who thinks it gets lower? Who thinks the temperature gets higher? It gets higher, right? Because it gets energy, right? Shall we go back? So because potential gets shallower, CMB photons get energy, right? So the temperature goes higher, right? So let's try to find it by cross correlating. Okay? Then okay, so this is the result before my paper. Okay, so these people are writing papers, and actually, except this one, they are detecting around 2 sigma. The highest one is 2.8 sigma. But 2 sigma in astronomy is not so significant, right? So ideally, we want to go higher significant, more than 3 sigma. And to do that, we need wider data. We need more galaxies, and then deeper. We need more galaxies. So that's why I use the WISE, because it's all sky survey. Okay. Okay. I should have explained this, but this is WISE. It's a wide field infrared survey explorer, so it's near to mid infrared all sky survey. And then it's much deeper than IRIS. So if you start 3 order deeper than IRIS. So if you okay, sorry, there's no IRIS. Okay, there's no IRIS. Okay. Okay, so let's use this data. Then I only select galaxies, because stars are in a Milky Way, it's not related to any gravitational potential. Okay, so that's how I select the galaxies. And then this is another detail, just checking galaxy density. The functional coordinates b lambda beta. Then can you find? There's one problem here. Can you find it? Where is the problem? Or maybe I should magnify here. What's the problem in this plot? So this is plotting galaxy density as a function of b. So b is a galactic latitude, right? From the Milky Way plane, how many degrees? 0 to 90, 0 to minus 90. So what's the problem here?
Horizontal missing line in the galaxy density. That black
No. This is because we're counting galaxies. So sometimes it's not. There's no galaxy number. It's 1.5.
Oh,
it's just
okay.
1, 2, 3, 4, 5, 6. Anyone? Okay, maybe I should ask different way. So the red line, this is obviously plotting a median, is going down here, and here. It's going down slightly, right? Why is that?
Due to the galactic planes.
Yes. These are stars, right?
Yeah.
So the stars contaminating here. So that's a problem. So that's why I cut the data. Okay, there's a little bit, but then there's more here in a galactic plane, in a Milky Way galaxy. There are a lot of stars. So I masked out the data here. So that's what I did. Okay. Then, aside this, it's mostly uniform, right? So galaxy sample are so okay. Then redshift distribution, it's something like this. So this is which one? I forgot. Okay, the red one is the redshift distribution of my sample. So most of them are actually detected with gamma. So redshift of my sample is 0.15 or something like that. This is needed when I detect a signal, I compare with the model, right? And to construct a model, I need to know the redshift. So this is just I'm measuring the redshift of my galaxies. Okay, and then the bias also I need to measure the bias because I'm using galaxy, not dark matter. So if the bias is the ratio in the difference in clustering between two underlying dark matter and then galaxy density. So galaxy is tracing dark matter, but it's not perfect tracer, right? It's not just 1-to-1, right? So there's a factor, difference is called this bias. Say. So I need to measure this again to do the model prediction. How do you measure this? You just take a galaxy correlation and then fit the model. So here these black points my galaxy correlation. So this is galaxy correlation. And then obviously small scale there are more correlation because galaxies are clustering with gravity. Okay, that's fine. And then theory. So I fit this curve, theoretical correlation to this data, and then I get bias is 1.06. Again, this is just this parameter is needed to construct a model of Sachs Wolfe effect. So I'm measuring it. It's a little bit. Okay, now I'm ready to cross correlate this. So I have galaxy density, I mask out the galactic plane, and then there's a CMB. In this, at this time, Planck data were not available, so WMAP CMB data are the best data. Okay, and then I measure cross power, and then errors are estimated Monte Carlo estimation. I did it 1,000 times, so that's hard. Let's see. Is there a signal? So this is what I got. So here I'm showing that this is a galaxy density, CMB temperature, power spectrum. Okay, again L. This is Fourier space. So large L means small scale, small L means large scale, right? And then my data points are here. Those blue ones are my data points. Errors are from Monte Carlo simulation. And then, so if there's no correlation, no integrated Sachs Wolfe effect, it's going to be flat, right? But as you can see, my data points are going up, right? Especially this one and this one are away from the flat, right? And then theoretical prediction. So if we assume the redshift distribution like 0.15, then bias parameter 1.06, then theoretical prediction of integrated Sachs Wolfe effect should be here. But then the best fit of the model is here to my data. So it is interesting. I detected stronger integrated Sachs Wolfe effect. Oh, first of all, I detected 3.1 sigma. So it's the most significant one at that time, and then above 3 sigma, so that's good. So that's good. And then there's no color dependence, no frequency dependence. So this VWQ is different frequency in WMAP data, CMB data. And then it's consistent result. So that's good because ISW effect shouldn't depend on the frequency. And the correlation is found. It's significant, 3.3 sigma. But then there's a remaining question why this is signal is higher than expected from lambda CDM, which I don't know the answer. Maybe some fluctuation of the signal or some exotic gravity. We need, we're not sure. Okay. This is more detail. Yeah, the delta chi-square is 9, and then likelihood is 97. So that's very strong evidence. So usually if this is 3 greater than 3 or greater than 5, it's significant. So my result is very, very significant. Okay, so that's good. So I detected the most significant integrated Sachs Wolfe effect in this paper. And then I wanted some students to do this, going to the 5 sigma detection of dark energy, maybe with using white full data or Akari, plus Planck data will be there. It's going to be 5 sigma because this data will be much larger than my data. So I was working on this with my student, but then that student graduated without finishing paper. So unfortunately, she submitted a paper, but then graduated, and then she just stopped there. Nothing. No, I sent an email. Nothing.
Maybe I can continue her project in the future.
You can, but then, please don't graduate before.
Okay.
Yeah. So, yeah, you can. If you're interested, you can. If you detect 5 sigma dark energy, that's something. Dark energy is important.
Nature paper.
I don't think ISW is going to be nature, but it's going to be important. Okay. Oh, by the way, because the first paper I detected the ISW effect was a nature paper.
Oh.
But then now we are increasing the Okay, so I finish here. Yeah, please remember that this ISW effect, that's the main topic of this today. Okay,